Okay, I'm going to talk about covalent bonding and Lewis structures. So first, covalent bonding is just sharing of valence electrons in order to attain octets. So you've got two or more atoms that can come together and bond and form a molecule. And in this process, they share valence electrons. And the way that things come together and bond is going to be dependent on these things attaining octets, or most often. Um, so when this all happens, what happens is electron pairs form. Okay, now within an individual atom to start with, there are some electron pairs already present, but when the bonding occurs and you form these molecules, you're always going to have paired electrons, unless if you had a scenario where there was an odd number, which is unusual, so we're not going to look at that right now. But when we have these pairs of electrons, we have two different types. You can have bonding pairs of electrons, where those are the electrons that are shared between two atoms, and they're pairs, so they come in twos, and so those electrons will be shared between two atoms. You can also have non-bonding pairs, and so those are not part of a bond, and so we also call them lone pairs, and so those are ones that only belong to one atom within that structure. Okay. And so when we represent these in a Lewis structure, the bonding pairs we represent as a line, and that line is between the two atoms that it's being shared, connecting those two atoms. And then the non-bonding pairs we write out as dots. Okay, so there would be two dots to represent a non-bonding pair or a lone pair. Now, with the bonding, we can have three different types of bonds. You can have a single bond, you can have a double bond, you can have a triple bond. Okay, and each one of those we just represent with lines. And so a single bond is one line, a double bond is two lines, a triple bond is three lines. And each line represents two electrons, or a bonding pair. So a single bond being one line is two electrons being shared between the two atoms it is connecting. A double bond, which is two lines, is going to represent four electrons being shared between those two atoms. Whereas a triple bond being three lines is representing six electrons being shared between those two atoms. Now, let's talk about Lewis structures. So if we wanted to actually draw a Lewis structure, specifically of a covalent compound, you can draw Lewis structures of ionic compounds, but they don't give us a ton of information, so we don't do that very often. And it's really not very complicated. It's just moving electrons from one thing to another. Whereas in covalent compounds, you have this sharing of electrons, which isn't always immediately obvious from just the individual Lewis symbols. And so the way things share electrons can vary from one compound to another. So what I'm going to do is go through kind of a list of guidelines on how you could draw a covalent compound's Lewis structure. Okay, and if you follow these steps, if you really follow them in order given and follow through with each step, then you should always be able to come up with a valid Lewis structure. Okay, and so a valid Lewis structure is something that represents, what is going on in this structure, but it may not be the most stable representation. Okay, so sometimes a molecule can be represented in multiple ways using Lewis structures. And there could be one of those ways which is much more stable than the others. But right now, we're not focused on that. Right now, let's focus on just drawing a valid Lewis structure, or one that is considered a correct Lewis structure. So to start, what you would do is first calculate the total number of valence electrons. And so to do this, all you do is add up the valence that each atom brings into the structure. So if you have, say, a carbon atom in the structure, that brings in 4 valence. Or if you have an oxygen, that brings in 6 valence. Or if you have a hydrogen, that brings in 1 valence. Okay, and all of that information you just get from what group in the periodic table an element is in. Now, one thing that can be a little confusing at first when you're determining the number of valence electrons for something is if there is a charge in my computer. Okay, there we go. If there's a charge, meaning you have some sort of polyatomic ion that you're trying to draw the structure for, you have to realize that the reason there's a charge is because there's some electrons that have been added to this or have been lost by it. Okay, so if something has an overall negative charge, it has additional valence, okay, in addition to what the individual atoms bring to that structure. Or if it has a positive charge, that means all of those valence that were brought in, it could have lost some, okay? So you always have to take that into consideration. So not just adding up the electrons each atom gives you, but if there's a charge, then you either lose or gain some of those electrons. And once you have that, what you should do is you should write out the skeletal structure of the molecule or ion, okay? And what I mean by the skeletal structure is you write down the element symbol for each atom in that structure, and you connect them, okay? And so you connect them each by a line, okay? And so everything always has to be connected in a Lewis structure. And so you would start with just individual lines, so single bonds to connect those things, okay? And another thing, normally what we're looking at are structures where you have just one central atom. So usually you have to figure out what's in the center, and then the only other things are just coming off of that central atom. So once you know what's in the center, you just draw a single line to each other thing that is there, okay? So if you're trying to figure out what is in the center, it basically is whatever's the least electronegative atom, okay? So you can look at the periodic table, and things that are further to the bottom left are less electronegative. Although sometimes, occasionally, that doesn't quite work out. And so I give you a list of atoms that actually favor being terminal. And when I say terminal, I mean outer atoms. Okay, so not in the center. And that would include hydrogen and oxygen and the halogens. Those are things that are rarely central atoms. The only time they're central atoms is when they're bonded with only these things. So when you have halogens bonded to other halogens, of course one of them has to be in the center. Or if you have hydrogen and oxygen bonded together, of course something has to be in the center, okay? So you can't have no central atoms, okay? So with this, it just gives you kind of a ranking. So hydrogen being first in that ranking means hydrogen is going to kind of trump everything. It's on the outside always, okay? You can't have hydrogen bonded to two things. Hydrogen only forms one bond, okay? Whereas pretty much everything else is going to want an octet, meaning could form up to 4 bonds. And then next up is fluorine. So fluorine's the next thing that's going to be on the outside, and that's because fluorine's the most electronegative atom. And then you have oxygen, chlorine, bromine, and iodine. So that gives you kind of your ranking. If these are the only things in your structure, those have to be on the outside. And in that order, okay? So if you only have that stuff, then the final thing in the list is going to be your central atom. Now, luckily, most of the time when we write our chemical formulas, they're written in the order of least to most electronegative, most often. So usually the first thing written is the central atom. So that's another kind of easy way to figure it out. The only other thing is sometimes you do have more than one central atom, but usually that's organic compounds, okay? And so that's carbon-based compounds. And so normally that would involve like a chain of carbon atoms. And sometimes that chain will have maybe an oxygen in it or nitrogen in it. And so those can be a little trickier. So usually the way people write them can help hint to you what how things are bonded. And so they'll list clusters of carbons. Um, but we're going to start with just having a central atom and everything coming off of it. Okay, so you got to figure out what's in the center, and you single bond everything. Now, once you're done with that, you're going to distribute the remaining electrons. Okay, so remember, you added a single bond to connect each thing, and so those single bonds are electrons. So each one of those is two of your valence that you have to work with. And so whatever you have remaining out of your total, you're going to distribute those. And there is really a way you should do this. You should always start with the terminal atoms, meaning the outer atoms. Okay, so you don't start in the center. It will make your life the easiest if you add enough lone pairs to all of the outer atoms to give them octets. Okay, or at least until you run out of electrons. If you run out of electrons before you fill the outside with octets, you have to stop. Okay, but if you still have electrons after you've put an octet on all of the outer atoms, then you're going to put those on the central. Okay, everything left over, even if it causes your central atom to have more than 8. And so occasionally that does happen, but most of the time you're going to be focusing on giving everything 8. You definitely don't give, more than 8 electrons to an outer atom. And don't forget, any bonds to an atom count as 2 electrons. And so you don't add 8 actual dots to everything, okay? Because some of them are bonds. Now, once you're done with that process, once you have all your valence on the structure, don't add extra, okay? But then you need to check, does everything have an octet? Okay, does everything have 8 electrons? And if there is anything that doesn't have an octet, of course, with the exception of hydrogen, okay, hydrogen can only have 2, so hydrogen should have a single bond and that's it, no lone pairs. But if there's anything that doesn't have an octet, what you would do is you would take from something that does, and you'd take a lone pair from it and you'd make it into a double bond or make it into a triple bond if you're shifting even more electrons. So you never add extra bonds until you need to, okay? And usually, if you follow this process where you fill the octets on the outside, the thing that's going to be lacking is the central atom. And so you can choose from any of the outer atoms and you just shift a lone pair and make it into a bond to the central atom instead. And what happens is the outer atom still has its octet and the central atom gains an octet. And so that's where you'll end up getting double and triple bonds, is by kind of fixing things in the end. I would recommend never start a structure with double bonds and triple bonds because it can mislead you, and sometimes it can feel like you never can get a right structure then. So you should start with single bonds. Okay, now this process should always lead you to a valid structure, as I said. So something that is correct, it may not be the most stable, but that's okay. You've got to be able to get a valid structure to be able to do the future steps that we get from Lewis structures, and that would be to then start predicting shapes of these molecules so that then we can start understanding the macroscopic properties. So let's go through some examples of drawing Lewis structures. So this first one, we'll start simple. This is just a 2-atom structure. So O2. So this one's pretty simple, but we're going to go through the steps and make sure you understand the steps. So first is calculate the total number of valence electrons. Okay, so we have 2 oxygen atoms, and each oxygen atom gives you 6 valence electrons. So we have 2 times 6, which means we have 12 valence electrons to work with. And now we're going to write our skeletal structure. And since it's just 2 atoms, it has to be oxygen bonded to oxygen. So we don't really have a central atom in this case because it's very simple. Now I say distribute remaining electrons. Okay, so right now there's one line, meaning 2 electrons. So I've used up 2 of my 12, so now I have 10 left. Okay, and so then I'm just going to start filling octets on the terminal atoms, which in this case are both of them. And so I'm just going to start at the left. You can start at the right if you want. But what I need on this oxygen is 3 lone pairs. So if I add 3 lone pairs to that, now that oxygen has an octet because it has one bond, which is 2 electrons, and it has 3 lone pairs, which is 6 electrons. So it has a total of 8, or an octet. So now I've used a total of 8 of my 12 electrons, and so I have 4 left. And so 4 gives me 2 lone pairs. So I can put 2 lone pairs on this other oxygen. But at that point, I am out of electrons. I have no more. So even though that oxygen doesn't have an octet, I can't just add 2 more dots, okay, because we don't have them. And so for this, now I'm at the point that I do have an atom that lacks an octet. So I need to take from something that has it, meaning that oxygen on the left, and share with the thing that doesn't have an octet. So what I'm going to do is I'm going to take a pair and share it. So I'm going to get rid of that lone pair and make it into a double bond. So then I'm going to have a double bonded oxygen, okay? And then I still have 2 lone pairs on the left side, and I still have 2 lone pairs on the right side. All I did is shift those 2 electrons and share them instead of put them only on one atom. So I still have 12 electrons. Both of those oxygens have an octet because both have 2 lone pairs, which is 4 electrons, and 2 bonds, which is another 4 electrons. So both have access to an octet. Now keep in mind that double bond, we're double counting those 4 electrons, okay? So I don't really have 16 electrons in the structure when I'm counting 8 for both, but some of those are counting for both atoms have access, okay? Okay, so this would be our structure for O2, okay? Now, let's do another one. And we have another pretty simple one, O2 2 minus. So this is actually the peroxide ion. And so the peroxide ion, we've got 2 oxygens, each one of them has 6 electrons, and then we have a -2 charge, meaning it has 2 additional electrons. So in this case, I have 14 electrons. So I still have the same skeletal structure, oxygen bonded to oxygen, but right now I have 12 electrons to work with. So I can add 3 lone pairs, or 6 of those 12, to the left side, and then I have 6 left, so I can add those other 6, to the right hand side, okay? And so when I do that, now I have 14 electrons on that structure, and both oxygens have an octet because both have 3 lone pairs, which is 6, and both have a single bond, which is 2. So both have an octet. Now the one thing I'm missing is that there's a charge on this. Whenever there's a charge, I have to indicate that. And so I put it in brackets and put a 2 minus there to indicate overall that structure has a -2 charge. Okay, so it is a polyatomic ion in this case. And so that would be my Lewis structure for the peroxide ion. Let's do some more. Now let's do Cn minus. So I think this is the last kind of simple one, just 2 atom one that I have for you. So for this one, I have carbon. Carbon has 4 valence, and then nitrogen is 5. Okay, and again, you get those from the periodic table. So carbon's in group 4, nitrogen's in group 5. And then I have a negative charge, so it has 1 additional electron. And so this gives me a total of 10 to work with. And so for this, I have a carbon attached to nitrogen. And then I've got, 8 more electrons to work with. So you just pick a side, doesn't matter. Normally you're going to have a central atom and outer ones. You just pick one of the outer ones and you start with it. So I'm going to just go ahead and start with carbon. If I do that, I can put 3 lone pairs on there. And so now I have 2 electrons left. And so those I'm going to have to put on the nitrogen because it still needs electrons. So now I have 10 electrons on my structure, but I have a problem. My nitrogen only has 4 electrons because it's got 1 bond and 1 lone pair. And so it's lacking. And so what I need to do is I need to take from the thing that has an octet, which would be our carbon. And so I could take 2 of those and share it with nitrogen. And if I did that, then I would get C double bonded to N. I would have 2 lone pairs still on that carbon, and I would have a lone pair on the nitrogen. But now if you count, you've got carbon, it's got an octet, 2 lone pairs, 2 bonds. Nitrogen only has 6. It has 2 bonds and a lone pair. So it's still not good enough. We need to keep going. And so I can take another pair from my carbon that has an octet and share it with nitrogen. If I do that, then I get a triple bond to nitrogen. I still have 1 lone pair on carbon, 1 lone pair on nitrogen, and so that structure, it has 10 electrons in it. The carbon and the nitrogen both have access to an octet because they both have a triple bond and they both have a lone pair. Okay, so that totals up to 8 electrons for each. And then the last thing I need to do is indicate the overall negative charge. So I put it in brackets and give it a charge. So that would be my Lewis structure for cyanide ion or Cn minus. Okay, so now let's move on to some things that actually have a central atom. Okay, so things that have more than 2 atoms are going to have a central atom. So we've got NH3. If we want to draw the structure for NH3, well, nitrogen gives you 5 valence, and then we have 3 hydrogens. Each of those has 1 valence, and so that gives us a total of 8 to work with. And so now I have nitrogen, and it's got to be attached to the 3 hydrogens, because remember, hydrogen is going to have to be on the outside, because hydrogen can only form 1 bond, and it can't even have lone pairs, so it's always going to have to be on the outside, okay? And so that by default tells us nitrogen's in the center. Also, the way it's written tells us nitrogen's in the center. So now I've used 6 electrons, so I have 2 left, okay? Now normally we put those on outer atoms to start with, but our only outer atoms are hydrogen, so now we're going to go to the center because we can't add those to hydrogen. And so I'm going to put those 2 remaining electrons on the nitrogen. And now we're going to look and say, okay, does everything have an octet? Or at least it should. Hydrogen can't have an octet, so we'll kind of ignore those. And then nitrogen's got 3 bonds. Each of those is 2 electrons. And then a lone pair, which is 2. And so we have a total of 8 in that structure. Okay, so that's good. That's our structure. Okay, let's do another one. Let's do the chlorite ion, ClO2 minus. Okay, so ClO2 minus, we've got chlorine, that's got 7 valence. We've got 2 oxygens. Each of those gives us 6. And then a negative charge, which means we have an extra electron. And so let's see, that gives us 20 electrons to work with. And so now I need my skeletal structure. Now, like I said, what's written first usually is the central atom. Also, if you remember that list of elements, it was hydrogen, then fluorine, then oxygen, then chlorine. Okay, so oxygen is going to favor being oxygen's going to favor being terminal because it's written first in that list, right? So chlorine is going to be in the center. So we have chlorine, and we have 2 oxygens. So that's my skeletal structure. Now, I've been writing these horizontally. You can write them vertically if you want, or you can have an angle in this. It doesn't matter how you kind of angle these atoms in the structure, because a Lewis structure isn't telling you the three-dimensional aspect of it. That's a step past Lewis structures. And so it doesn't matter how you're kind of drawing it flat, just so the connections are the same. Okay. So right now, for our skeletal structure, we've used 4 of those 20 electrons. So we have 16 more to work with. And so what I'm going to do here is I'm going to fill up the octets on the outer atoms. So I'm going to use 6 of the remaining 16 on one oxygen, and the other oxygen will also have 6 on there as lone pairs. And so now I've used, what, 16 total? So I have 4 more. So those will go on the central atom. Okay, so if I do that, it actually works out, and I already have an octet on everything, right? 2 oxygens have 3 lone pairs and a single bond, which is an octet. The chlorine has 2 bonds and 2 lone pairs, which is an octet. Okay, and I overall have 20 electrons, so that one's good, except I need to add my charge to it. Okay, so I put that minus on there. And so that would be a valid Lewis structure. Now again, keep in mind, we're going through and doing these steps to find a valid Lewis structure. Okay, so it gives you something that's considered valid, it follows all the rules, but it may not be the best Lewis structure. And we're not concerned with that at the moment. Okay, we don't actually need the absolute best Lewis structure to figure out what we need to know about the shape. Okay, so we're focused on find a valid structure. Once you get that, you can worry about, once you get really good at this, you can worry about finding a better one. Okay, let's do another one, PCl3. Okay, so PCl3, we have 5 for phosphorus because it's in group 5. And then we have 3 chlorines, each of them is 7 because those are halogens. Okay, and so that gives us a total of 26 electrons. And then in our skeletal structure, phosphorus is going to be in the center. The formula kind of hints that to you because it's written first. And also, it's not hydrogen or oxygen or a halogen. Okay, those things like to be on the outside. So the chlorine is going to be on the outside. So I'm going to attach 3 chlorines to that phosphorus. Now when I do that, I've used 6 of my electrons, so I have 20 more to work with. So I'll fill octets on my outer atoms. So if I put 6 electrons on each one of those chlorines, then that is going to be a total of 18 more electrons. So now I only have 2 left. So those 2 will go on the central atom. Okay? And now we check and see if everything's got octets, which they do. Your phosphorus has got 3 bonds and a lone pair, which is 8 electrons total. And then each chlorine has 3 lone pairs and a single bond, which is 8 as well. And so that would be a correct structure. Now I know several of these that I've done, it's come out, you follow these rules and you don't even need to worry about the last one, right? And that's great. But you do have to still consider that. Sometimes you do have to make double and triple bonds. But if you follow these rules in this order, I think you get to the correct one quicker, and you make less mistakes. Okay? Don't try to memorize structures or look them up. If you look them up, sometimes you find wrong structures. You got to be careful. So if you follow this set of rules, you'll always get to the structure. Okay, let's do another one. NH4 plus, so the ammonium ion. And so nitrogen gives you 5 valence. We have 4 hydrogens, each one gives you 1. And then we have a positive charge. Now, a positive charge is formed when something loses electrons. So we've actually lost one of our valence. Okay, so this one's going to have 8 electrons. And then our skeletal structure, nitrogen is going to have to be in the middle because hydrogen cannot be in the middle. So we have 4 hydrogens coming off. And then when we do that, we have 4 bonds. 4 bonds is 8 electrons. So we've already actually used all our electrons in this. We're not actually going to add any dots because we don't have any more electrons. And so hopefully that means everything's okay, right? So our hydrogens have 1 bond and that's all they can have. And nitrogen's got 4, which is 8 electrons, so it has an octet like it needs. So now all I need to do is indicate the charge. Okay? So let's see. I think I've got maybe one more. Yeah, one more for you. We'll do this last one. And then if you need more practice, you can always look up more videos or, open a chemistry book and find some practice. Okay, this last one we've got is CH2O. So we've got carbon. It's got 4 valence. We've got hydrogens. So 2 of those each gives you 1 valence. And then we've got 1 oxygen, which gives you 6. So that gives us a total of 12 electrons to work with. And based on the formula, this is kind of hinting that carbon's in the center, right? And also hydrogen can't be in the center and oxygen doesn't like to be in the center. So that also kind of leads you to that. So we're going to have 2 hydrogens coming off of it and an oxygen. Okay, now we've used 6 of our 12 electrons, so we've got 6 more. And so my outer atoms, I've got hydrogen and I've got oxygen. I cannot put the electrons on hydrogen because they can only have 1 bond, no lone pairs. So I'm going to put 3 lone pairs on the oxygen, and that is my other 6. So now I have 12 electrons. So I'm out. I can't add any more. And so then I check for octets. So hydrogen can't have an octet, so I skip that. But my oxygen, it has 3 lone pairs and a bond, so it has an octet. But my carbon only has 3 bonds. That's only 6 electrons. So my carbon needs more. Okay, so I take from something that has an octet, okay, and it has lone pairs and shift it. So that would be my oxygen. My oxygen has enough. So what we can do is we can share those 2 instead of keeping them just to the oxygen. So if we do that, we're going to still have those single bonded hydrogens, but we're going to have a double bond to the oxygen, and then that oxygen is only going to have 2 lone pairs on it. And so that structure still has 12 total electrons, but now the carbon and oxygen have octets, okay, like they need to have to be a valid structure. Okay, so that would be our Lewis structure for CH2O.